No? We've got full electron configuration for manganese. What is the full electron configuration for manganese going to be?
1s2, 2s2, 3p6, 3s2, 3p6, 4s2, 3p5.
Yay. 2. There we go. All right, and then from here on out down here, I'd like to do the abbreviated electron configuration for them instead. What do you got? Yes, sir.
For manganese, I got AR 4s2 3d5.
And for zinc, R and
4s2 3. I'm gonna guess 10, but I feel like I know that's wrong. But
nope, it's correct.
Wait, it is?
Yep.
Stop second guessing yourself.
All right, and if I were to go about drawing the orbital diagrams for each of these,
I don't know how to do this.
that's why we're reviewing.
Oh wait, yes I do actually. Wow.
Talking with your mouth full is not preferred.
But she's not even talking. She's like,
Mumbling and yes.
her mouth isn't even open.
I remember watching this thing
Mumble
in the
rapping.
house.
Yeah, the bunk beds. You
Oh,
were
right.
beds in the hotel.
So we have the orbital diagrams that are drawn there as well. You might remember from your first chem class or from earlier this year that we had talked about lithium, sodium, potassium, rubidium, cesium, francium. All those end up having a positive 1 charge anytime they make a compound. Okay, they're either 0, they have an oxidation number of 0, or they have an oxidation number of positive 1. Then we said the oxidation numbers for fluorine, chlorine, bromine, iodine, acetine are usually a negative 1, but sometimes in certain circumstances they can be something else as well. Right? But then we said the transition metals is just a mess. Right? And we said with the transition metals you can have more than one type of charge. Okay? And then even after that we said, well, while the transition metals as a whole end up being a mess, zinc, cadmium, and silver always have the same charge. Not necessarily as each other, but for example, zinc and cadmium always have a +2 charge, and silver always has a +1 charge. What I'd like you to do is take a look at the orbital diagram and the abbreviated electron configuration that I've written up here for zinc. And can you, with your partner, discuss why zinc will always have a +2 charge when it forms an ionic bond? Talk about it with each other, see what you come up with.
Isn't it because the +2 substitutes to electrons? So it's because the S or S, it's easy for it to lose because it's out of the side.
You have to valence electrons before us.
Because science.
Yeah, right now my mind is just like,
I took a 4-hour half.
All right, folks, what'd you get?
Science.
science.
Yeah,
That's the best explanation I got. That's the best explanation I got.
Because
So,
Valence electron.
let's ask it, which valence electrons? The 4s. Which electrons are going to get lost first? The 4s. Why are the 4s electrons going to be the ones that get removed first? You remember me bashing knuckles into Rosha's head. So, if I were to stand by Rosha's head and hit him in the head consistently with my hand, which particular portion of my hand is making contact with which particular portion of his head?
Skin.
Skin to skin. So the outside energy level, in this particular case, ends up being the 4s. The 4s is the outermost version. And that means these 2 electrons are going to go away. And if those are gone, now I'll have zinc with a +2 charge would be Ar. 4s0, 3d10. Do you have to include the 4s0?
No.
No. College Board might, depending on the question, and I want you to be aware of that. And then what would the orbital diagram look like? Well, for the atom it ends up looking like this, but for the ion, it looks like this. So here's the abbreviated electron configuration for the ion. Here's the abbreviated electron configuration for the atom. Here is the orbital diagram for the atom. Here it is for the ion. Why is it not likely for zinc to have a positive 3 charge?
So I have to take from the 3D.
We'd have to take from the 3D, which are closer to the nucleus. And what do we know about electrons that are closer to the nucleus? They're harder to remove. Remember when we talked about decreasing the distance between the positive charges and the negative charges? The less the distance, the much more energy is needed to remove those electrons. Okay? If they're further away, the much less energy it has, because it's going by the inverse squared law that we had talked about. So, and again, you don't necessarily have to know about inverse squared law, but you should know the distance drops off pretty quickly. Where would those electrons go? Talk about it with each other. Where would electrons go if they're getting lost off of this? Where are they going to go to?
In the board.
There's
Whatever.
Whatever it provides.
Yeah.
left there.
They like eat it. Wait, is
That's not the proper term.
is this?
That's not the proper
No, that's a
term.
scientific term.
No,
They
that's
get
not the,
yeeted.
that's not the proper tense
In
for
Mach
it.
6.4.
No, they get
They yelled it.
Who's in that
They get
mistake?
yoked.
Mach
They
6.4.
yolk.
Mach 6.4 of electrons.
Okay. Where are they going to go?
There.
To another
To the moon!
element.
NASA.
Or another atom.
To another.
Ion. Create an ion.
How about this? What is going to pull the electrons away from the zinc?
Another
Attraction.
another element. Or another part of atom.
A
Electron,
positive,
right.
a positive charge.
Thank you.
Thing.
Something that ends up having a high enough positive charge to be able to pull it. So what is going to have a high enough positive charge to make that happen? Well, something that is going to have enough protons, but not enough electrons. Okay? Can we come up with an example of an element that ends up having more than enough protons, but not enough electrons to make that work?
Calcium.
Calcium would not be that case.
Uranium, 238.
Going way off the periodic table.
Chlorine.
What's that? Chlorine. Let's start simply with chlorine. What's the abbreviated electron configuration for chlorine? Abbreviated
Oh,
electron config for chlorine.
wait, what was the
Neon,
question? 3s.
Right now I'm asking, what is the abbreviated electron configuration for chlorine?
neon,
Me.
neon,
3s2.
3s2.
P5.
P5. And then the orbital diagram. P orbitals end up having 3 lines. Whoa. So where is this electron going to go?
there.
And when that happens, this chlorine now is going to become a chloride ion or a Cl-, which would then become 3s, 3p.
So wait, when zinc and chloride are in a compound together, or like does the chloride just absorb the? I'm confused why.
So let's talk about what's going to happen.
So is this like
Chlorine has the ability. Chlorine has the ability. It has enough protons in it to be able to attract electrons from something else.
Right.
Great. So when it does that, it has more energy. It has a stronger ability to attract that electron than zinc does.
Right.
So it just completely gets absorbed by that chlorine.
Right.
When that happens, the chlorine atom becomes a chlorine ion. Great. What charge does this now have?
-1. because
Negative
you have
1.
an electron.
What did the zinc do when it lost the 1 electron? It now has what? A positive 1 charge. What's going to happen to this positive 1 zinc and this -1 chlorine?
Doesn't attract.
Those as ions are going to attract and stick together. Great. Zinc is not necessarily in its most stable configuration yet because we've already said that zinc is going to be more stable as a positive 2 charge when it has completely emptied out that 4s orbital. What else has to happen to that second electron?
It has to get pulled off by the chlorine.
By a different chlorine. Can it get pulled off by this chlorine?
No.
No, because it's already got filled up. So if I do this entire thing times 2, right? Now what you end up having is ZnCl2.
Is this like bonding or something?
This is starting of bonding. Bonding is truly going to be the next 2 chapters after this. This is the lead up to it.
So
Question?
why
Yeah.
would
So if
so
it's-
this is just if you throw, let's say, chlorine and a zinc atoms into each other and put them in a giant container, then they end up making zinc Cl2.
Yes,
Wait, so if it's
zinc chloride. One of the ways that I could do that is if I just took a chunk of zinc and dropped it into the hydrochloric acid. Right? The zinc is going to start losing electrons. The electrons are not, in that case, going to be going to the chlorine. The electrons in that case are going to be going to the hydrogen instead. So you might remember if I take, I'm just going to write this off on the side over here, Zn plus HCl, predict products balance equation.
Would be the
ZnCl2 plus
H plus.
H2. 2HCl would be the balanced equation.
What is hydrogen?
So what happens when we talk about states of matter? This is solid, this is aqueous, this is aqueous, this is gas.
But then wouldn't it stay as an ion?
What's the question?
Why does zinc turn back into metal? Why wouldn't it just stay as an ion? Because in this case, it's hydrochloric acid, so it should just stay as a H plus ion, shouldn't it?
So in this particular case, what if we were to keep going from here? I'm going to get rid of this. I'm assuming people don't need it anymore. If we were to go from here and write out the net ionic, or the complete ionic equation, zinc is a solid, so it does not change.
Right.
I would have 2H plus 2Cl minus going to Zn plus 2 plus 2Cl minus plus 2H2 gas. So what happens?
Wait,
The
what is
chlorine is what? Did its chlorine change? No. Those would be spectators. So what you'd end up having is zinc plus 2H plus going to zinc plus 2 plus, not 2HCl, 2, it's just going to be H2. H2 gas. So where'd the electrons go? They left the zinc and they went to the hydrogen. Let's get back to this example, because I think I confused you with this example. Just mental flush that for right now. Going back to this. If I had elemental chlorine, not even worrying about the fact that it's diatomic chlorine, because that'll mess people up even more. Just elemental chlorine, Cl on its own, and I have hydrogen and zinc on its own. Zinc is going to do what with electrons? It's going to get rid of them. Why did it get rid of them? Because this was able to do what? It was able to attract the electron and pull it away from the zinc. So far so good? Okay. How many electrons are the atoms of zinc going to be getting rid of? 2. Great. That means how many chlorines would I need to make that happen? 2. All good with this so far? Okay, next question. What's going to happen to the size of zinc when it goes from Zn to Zn2+? And what is going to happen to the size of the chlorine when it turns from an atom into an ion? Talk about it with each other. What happens to the atomic radius or the size of those things when they go from atoms into ions?
Yeah.
That's why I didn't
She says that she wrote it.
Okay.
No. I'm an emotional.
Zinc is going to do what? Get bigger, get smaller. Why? It's losing its orbital. Let's make sure that that's clear. 4s is bigger than 3d. Right? So if I completely get rid of both of those electrons, is there anything to make up that sphere? Which now means 4th energy level is gone. It's now smaller. All we're looking at is energy level 3. What's going to happen to chlorine?
It's going to get bigger.
It's going to get bigger. Why? This is harder. The explanation of why it gets bigger is more difficult. Yes, sir?
Because it gains an extra electron.
Okay, so if it gains an extra electron, here's one of the catchy things that we had talked about last week.
It pushes all the electrons out, right?
What pushes all the electrons out?
The extra electron that was added because they repel each other, so therefore it would
So the reason it gets bigger is because that one electron is repelling the other electrons in that same cloud, and it gets slightly larger. We all good with that part so far? Okay. What can you tell me about the force of attraction of the protons to all 6 of these electrons? It's equal, right? All of these have an equal attraction to the protons, but these are also going to be repelling each other, and that's what's making it a little bit larger. So the reason that that got smaller is because I emptied an entire orbital and that level is gone. The reason that got bigger is because the extra electron is going to repel the other ones, and that makes it all a little bit bigger. They all got a little bit further away. Yes, sir?
So proportionally, the change in size in zinc is a lot bigger than the change in size in chlorine.
That I do not know off the top of my head. I'm not putting any quantitative numbers to this to say definitely this one's going to be a bigger change or a different change. Because bear in mind, this is already pretty drawn in tightly because of the number of protons compared to the number of electrons in that outer ring. Granted, it's equal, but there's a strong draw to draw those in closer to the nucleus. When I put this in there, there's going to be a push to push that out. Is that bigger or less than that? Well, remember the 4s is not that far away from the 3rd energy level. It might be, but it really depends on which one we're looking at. So there's no good way to describe. That would not be a question that would show up. Which would have a bigger effect? Right? Unless there was an obvious explanation to it. This would not be so obvious for information. I know last week one of the things we discussed was differences in atomic radius. So let's take a look at those differences in atomic radius, and here ends up being a chart of atomic radii. What I'd like you to do is, can you explain the trends? This one you should already be able to do. What happens?
I know this one.
Go ahead. Go for it.
Okay.
You want to discuss it? Go for
As you
it.
go down the column, no, that's a row. That's a row. That's a row. I know that. I know that. I know that.
Okay. Just say up, down, left, right. Let's start that way.
As you go to the right of the row,
Yes.
the radii get smaller because the number of protons. No, it's because the smaller increase in radius is like area. Wait, I know this. wait.
Increase
Okay.
in radius
Yes, that.
has a bigger
Okay.
increase in surface area.
Volume. It's volume.
Okay.
It's something about the attraction of the electrons.
I thought you did.
You know, right now you have just reviewed all of last week into the end and the answer of one explanation, but it didn't necessarily make any sense because it was all disjointed and talking about different things.
Can I explain it?
Give it a shot.
Okay, the reason that the electrons are initially smaller in the left-hand side of the periodic table versus the right-hand side of the periodic table is because they have the same number of rings, and I know they're not rings, but I'm calling them rings because I don't have another word for them. They have the same number of rings, but they have less protons to attract those rings in closer, so the further you get down the row, the more protons they have, the more attractive it is, and the more it will pull them in.
Okay, let's pause there. So, summary. As you're going across the periodic table, you are in the same energy level. Okay, so instead of using the word rings, we are now in the same energy level if you're going across the row. If you are in the same energy level and you add protons, what happens to the size?
It decreases.
It gets smaller. Why is it getting smaller? Higher Coulombic attractions from the positive charges to the outside electrons, making it smaller as you go across the row because of the addition of protons. What about going down a column?
It's bigger.
Why?
Because there's more energy.
There's more energy levels. You're adding additional layers to the actual atom itself, so the atoms are going to be getting bigger. So if you have not written down, by the way, the atomic radius trends in your notes someplace, you probably should write those down, and the explanation to why. As you're going down the columns, you are adding additional energy levels. And then as you're going across the row, it's getting smaller because you are adding additional protons and keeping the energy level the same. All right, so here's the next thing that I want to point out. And one of the things we could compare ends up being the two that we did the atomic structure for and basically talked about the abbreviated electron configuration. If I were comparing manganese to zinc, they're 5 elements away going across the row. And if I were to compare, let's say, 5 elements in the second row, which is now at 167, and I'm now going down to 56. This thing dropped almost by a third by going 5 elements across this way. However, when I drop 5 elements across this section here during the transition metals, I went from 161 dust down to 142. And as a matter of fact, if I compare all of those in that row, really?
Oh, possessed.
That was exciting. Let's try that again. That was
That was
weird.
weird.
All right, I'll have to calibrate the board here in a second.
That was whack.
Let me try that one more time here.
Yes. That's so whack.
All right, so looking at those specifically, you will notice that the change in the numbers, yes, it does change. Yes, it's decreasing. It's following that same pattern that we've talked about for the past week. But why is the drop in them nowhere near as big as the drop that we got in other rows above it? Talk about it with each other, see what you come up with. Why is the drop in the D section here not nearly as big of a drop in radius as it is in other spots?
Because it's the third energy level.
Yeah, fit much more like
It gets smaller because it's on the same energy level, but there's more protons, so there's a higher.
versus the more electrons with the period supporting the interaction with the greater.
What was that last part? So there's higher.
Go across because you still have the same outer shell. Yeah, it's still the same like the outer shell, but you have more protons added to the center of it, so it causes the strength because it's more attractive.
I had to be.
I had C. 71%. I got a 65 on the Oakley.
Okay. Let's see what we got here, folks. Maybe I can go back.
Alright, cool, good. Nerd.
No, I did not.
Oh, yeah, no, I have like a 71.5 or something like that. He hasn't put it in yet.
That's why.
Okay, it's still a C, and I'm gonna keep it. Alright, I'm gonna take it.
You're gonna keep your seat. You're not gonna try to raise it up.
All right, folks, here we go once again. Why is the change in the radius across the row of d orbitals nowhere near as big as the drop when we're going across a row elsewhere? Yes, sir.
Well, it would be because it's proportional. So, like, there's the ratio between how much of the protons attract, cause it to attract each other in the initial parts of the periodic table is greater than when you get further down into it. So it doesn't affect the shrinkage of the ring as much.
There is a reason for that you have danced completely around him and have not touched. So, yes, your observation is correct, but your explanation is not there yet.
Okay.
Yeah.
Is this simply because it could fit more electrons in the energy level?
Which energy level?
The
Which D energy level? In the 3D energy level. Let me write this out. And again, have you noticed, by the way, that each time that I've been asking these questions that almost look like free response essays that you might find on your test on Friday, that I have been explaining them using abbreviated electron configuration and orbital diagrams to help understand what's going on?
Can we explain them like that?
Yes. As a matter of fact, what you need to do is probably draw one of these out and then write your explanation. Don't just write this out and assume that I know what you're talking about. You still have to put it into words. But using the diagrams would help. So let's go ahead and actually write out what the abbreviated electron configuration for all these elements would look like. Not all of them, but just generically. What is the abbreviated electron configuration going to be for those elements? Yes, sir?
Wouldn't it be just R 4s2 3dx?
4s2, 3dx. And where are the electrons going?
X.
Into the d orbitals. Of which level?
Third.
Third. Which one is defining the size of the atom?
First.
Wait,
Wait,
no,
what?
all
Wait,
of them.
Which
four,
of
four,
the...
4S.
Stop answering
Wait,
a question that you don't know the question yet. Of these two, which one of those two is defining the size of the atom?
4s.
Is it the 4s or the 3dx?
4s.
Both
The
of them.
4s. No.
I'm just trying
Why is the 4s determining the size of the atom?
Because it's on the
It's
other
higher.
It's further away.
But wouldn't both of them like?
I'm trying to give you the answer. Let me give you the answer, and then you can ask your question. Let me give the answer first. If I start dumping in electrons, where are the electrons going to go?
3
Into the 3D. Where is the 3D?
inside.
Inside. So here's this layer, and you're shoving more electrons further into the core of the atom. Is it affecting the size of that outside ring? No. So, why are these not dropping in radius nearly as much? Because where are the electrons going? They're going inside the atom, inside of a deeper layer, and not in really the outside layer of the atom itself. Do you have a question now?
Yes.
Go for it.
But wouldn't the 3D still affect the radius of the atom? Because
Yes.
if the 3D was not there, then it would then the 4s2 would wrap around closer onto the atom.
So, in taking a look, is there that effect? Yes. Is it as dramatic of an effect as it is in other places of the periodic table? No. So yes, there is a minor effect in the idea that I'm still adding more protons, and there are still going to be pulling in and getting tighter because of the additional layer of protons. However, if I were dealing with electrons that were going into the outer energy level, notice what happens is that when we're going across that, I'm getting just drops of like 5 or 6, where I'm getting drops of 10 to 20 in others areas. Yes, the atomic radius is still getting smaller, but it's not nearly getting as small because we're putting them into that core of the atom itself. So then the next question, where else on the periodic table will this happen while you're going across the row, adding more protons and electrons, and the size of the atom is really not going to get much smaller?
F.
The F block. Is it going to be more of an effect like this in the F block or less of an effect in the F block?
Less.
Why?
Because it's n-2.
Why is the n-2 important? Did I have a feeling? How many people understood what she meant by the n-2? Okay, so let's take a look at what we mean by the n-2. I'm just going to put it on whiteboard. Come, follow me. All right, so let me go ahead and draw out once again what we were just talking about with the D block before we go too much further. Here's the 1s, here's the 2s, here's the 3s, here is the 4s. Nucleus is in the center, sorry for drawing it so large. If I were to draw the 3D, I'm going to get rid of everything else that's around here. I'm going to leave kind of a portion of the 3s, so you have a decent idea of where it's supposed to be. This 4s has a shape. Is that going to be changed if I put in electrons in here? Very, very minorly. So this d orbital, if I put electrons into that d orbital, is it going to change the effect of the size of the s orbital? Not much. Same thing is going to happen if I put it in other of the d orbitals that happen to be in that section. All right, and that's one layer closer into the nucleus. What happens when we get to the F block? So let's do this. Let's write out the generic for all of row 6. What's the abbreviated electron configuration, generically speaking, for row 6?
It would be KR.
Xe.
Okay,
KR.
Wait, Xe.
Xe.
My bad.
Which one?
Xe.
Xe.
Sorry.
It's all right. Xe. 6s2, and then what? 4f, and I'm going to put question mark, 5d question mark, 6p question mark. Since we don't know which element we're stopping at the moment. What can you tell me about going through, let's say if we're looking at the periodic table, lanthanum, cerium, protactinium, neodymium, promethium, samarium, europium, basically I'm at 57 going across to 71. What's going to happen to the size, or where are those electrons going to go as we start to add them into those elements? Into the f orbital. Which f orbital? The 4f orbital. And the reason I mentioned the fourth energy level is here's 1, here's 2, here's 3, here's 4, here's 5, here's 6. Everybody with me so far? And that means I'm going to erase numbers 1, 2, and 3. If I start going into the 4F, now what I'm getting is that orbital that we talked about was really funky, don't have to worry about drawing. And where is it though? Here's the outside energy level. But I'm cramming them into this middle section in here. Is that going to affect the size of the rest of the atom? Not significantly. Right? So in the F block, as you're adding electrons, if I were to say which atoms are going to be more likely to be the same radius, samarium and europium, or phosphorus and sulfur?
Wait, sorry, repeat the question?
Samarium, 62 and 63 versus 14 and between 15 and 16.
What's the question though?
Which of those pairs would have almost identical radii?
61 and 62.
Okay, why?
Because they're cramming them into the center, and the radius is already so big that the addition of the extra electrons inside the atom will not affect the outside shell very much.
Everybody follow along with that? We have just spoke for about 10 minutes, betting not much got written down. Write something down to summarize the last 10 minutes. Yep.
This is a bit kind of unrelated but related. So
Okay.
if you had like, let's say lithium, but you got rid of one of the electrons, would the size of the lithium be even smaller than helium?
That's a funny question that you ask. We're actually going to be talking literally about that next.
Oh.
Not that exact element, but in a same series.
Okay.
Yep, that is exactly what we're going to be discussing next. And after you've had the opportunity to write some type of notes down from the last 10 minutes of discussion that we just had, I would like you to fill out that chart. What's the abbreviated electron configuration for the atoms? What's the abbreviated electron configuration going to be for the ion for each one of those 5 elements? Go for it.
What did the protein still have? I mean the proton.
All right, we are recording once again.
Woo! Thanks, Roche.
So, abbreviated electron configuration for magnesium. What do you have?
Ne3S2.
Ne3, S2. And this would be
Ne3S1.
Ne3S1.
Ne?
I'm going to go HE, 2S2, 2P6. You don't have to do it that way. I've chosen to do it that way.
Can
We're going to try and recalibrate.
Can we just not do Ne?
As I said, that is perfectly acceptable for an
Oh.
answer. I chose not to do it that way.
Okay.
No, Cyril. I'm used to saying no, Cyril. So not close though.
All right. So then for fluorine, what do we have for fluorine?
2S2, 2P5.
HE, 2S2, 2P5, and then HE.
2S2, 2P4.
Sweet. Any questions on those so far? Will neon form an atom? Or, excuse me, form an ion? No. How many protons does neon have?
Neon has
10 protons. And then an abbreviated electron configuration for neon, another way of writing it would be just writing neon in brackets. All right, so let's start talking about the ion possibilities for the ones that are listed. What about oxygen? What type of ion is oxygen going to form? What's it going to do? I did not ask what's its electron configuration. I just asked what's it going to do? -2 charge. It's going to gain how many electrons? 2 electrons, which would go into the p orbitals, which would then make He, 2s2, 2p6, which also is equivalent to Ne. How many protons are we talking about for oxygen?
8.
8 protons. Great. How many protons for fluorine?
9.
9 protons. And its abbreviated electron configuration is also going to be He, 2s2, 2p6, or you could write it as Ne in brackets like we had done in the last step. So what did you notice about all the electron configurations that we've got so far for the ions of fluorine and oxygen? They have what?
They're the same thing
As what?
as Ne.
As neon. So all those end up being identical to neon. What do we end up with for sodium? What happens to it to make it an ion?
It has to
Loses an electron. When it loses that electron, what ends up happening is that this one electron goes away, the third energy level is now completely gone, and you end up having Ne as your electron configuration. And the same thing's going to happen with magnesium, where you have Ne as the electron configuration. How many protons are we talking about in each one of those?
11 and 12.
11 protons for sodium and 12 protons for magnesium. Based on what we have just done, you should be able to tell me what's going to happen to the ion size of every single one of those pairs.
It's gonna go from.
So for magnesium, to go from magnesium from here to here, what's going to happen to the size of the atom as it becomes an ion? Gets smaller. We've got an ion going from sodium, or is an atom going to an ion for sodium will also decrease. Will sodium decrease as much as magnesium is going to decrease? Why not? In other words, which of these two are going to be smaller, the magnesium or the sodium, and why? Talk about it with each other. Which is smaller, magnesium or the sodium?
Magnesium has the highest.
Which one will be smaller, magnesium or Na?
Well, is there a larger difference in it losing two electrons or losing one electron?
So assuming that you have the... What can you tell me about the electron configuration between magnesium and sodium at this point? It's exactly the same. These two electron configurations are exactly identical. What's the only difference then when we're talking about its overall atomic structure? One proton. Is that one proton going to make a significant difference in the size?
Yes.
Yeah, because now you have a stronger positive charge on the same distance that is now going to draw them in closer to make it a shorter distance. So you'll notice that as we're going through, I could have used Ne for any of these.
Skadoosh might be laughing.
So, Sarosh would be appreciated. So with all of these end up having the same electron configuration as Ne or for neon, which would be, again, 2s2, 2p6. These are called isoelectronic. Those people writing it down, ISO, electronic, all one word. ELE.
Wait, what? Those are the ions are called isoelectrons?
So right now, if you have two substances that have exactly the same electron configuration,
Okay.
they are isoelectronic. So that entire second column where I have the abbreviated electron configuration for the ions, and I'm comparing them to the atom of neon, just to make sure that people are aware, this is not an ion. If I'm looking at all of the ions or the atom of neon, all those are considered isoelectronic because they have the same exact electron structure. But I should be able to have you tell me which one's going to be the biggest and which one's going to be the smallest and why, which is the next question I'm going to ask. For this isoelectronic series that we're looking at, which one ends up being the largest radius, which one has the smallest radius, and why? Discuss.
The smallest radius might be magnesium, and the largest radius would be oxygen. And protons is the same number of radius as protons, so it has to be subtracted twice by the electrons.
We're looking at the isoelectronic series, which would be the last column.
Oh.
Oh, that last
I don't know, I always explain things when I'm not sure when I'm...
Which one's the largest, which one's the smallest?
Goes down.
I see. I have a spray bottle.
We answered which one's the smallest.
All right, folks. If we're looking at the isoelectronic series of that second column of 4 ions and 1 atom, which one ends up being the largest? Denise?
Because oxygen is freezing.
Oxygen because it has the least number of protons. Great. And then the force of attraction is going to be weaker, meaning that the atom itself, or the ion itself, is going to be larger. What can you tell me about the largest? Which one's going to be the largest? Yes, sir?
The smallest or the largest?
I'm sorry, the smallest. I excuse me.
Okay, no, you're good. Magnesium. It has
Magnesium.
the most amount of protons and it's the same, what's it called, has the same amount of energy levels, so therefore it would have the smallest one because it has the largest force of attraction.
Right, so every single one of these has 10 electrons all the way through this entire list. If all these have 10 electrons, but these have more protons, you can tell what's going to happen with the size. As far as this is just a picture that's actually describing that isoelectronic series that we're just looking at, and their their ionic sizes compared to each other on what's going to happen. Nothing too surprising at this point, hopefully, but just a visual that you can see with it. Okay, take a moment to try and absorb this one.
I want to die.
There's a lot there.
In PM at midtime.
Picometers.
Picometer?
Right.
Pico, that's like 10, wait no.
10 to the negative 12.
12.
Or nice, I mean,
It's pinko.
It's Pico de Gallo. Wait no.
You all are giving me flashbacks to atoms, and I don't like it.
I want to die.
Atoms.
I hope so. Yes, you can.
Is that really loud?
I get issue with can.
You can do that, just go all the way to the end of the
I
thing.
mean, it's so common.
So,
Okay.
Heavy.
I like to
Do we want to deal with the red side or the blue side first?
I want to deal with
Which one is
neither.
less painful?
Both of them are about the same amount of pain, but they're really not that painful once you start to see what it
I
actually
like
is.
Jafari, can
Don't
you
even
see
know where to look.
if it's yellow or blue?
Well, let's start with
Are they
lithium.
red or
Take a look at the very first box. Very first box, we got Li+. And what's the size of Li+ going to be? What's the measurement going to be in picometers?
90?
90. Okay? What can you tell me about lithium as an atom?
It has, I don't know.
134. In the same exact box where you see the lithium plus at 90,
yeah.
the other half of it is lithium as an atom, which ends up being then 134. So now if you're comparing all those that are in red with the gray next to it, the red is what? The gray is what?
The red is the
Red
ion
is-
that creates the atom.
Correct.
On the right side.
So in general, when something becomes a positive charge, what happens to the size?
It
It gets smaller. Okay? So now that we have that cleared up, what's going on the blue side?
the opposite.
The opposite. You'll notice that the atom portion, though, this time is on the left, and the ion portion is on the right.
So when an atom turns into an ion and it has a positive charge, it will decrease in size. But if an atom turns into an ion with negative charge, it will increase in size.
Correct. And you should be able to give an explanation for both cases. Here's one of the things that I wanted to mention, by the way. Have you noticed that with all of my discussions of atomic radius and ionic radius and all that other stuff, I have not just been talking about electrons only. What have I been talking about as well aside from electrons? Protons. You need to mention both. Okay, when you're actually doing the essay questions for these, you need to mention both the protons and the electrons that are being changed, because that's really what's causing the effect overall. So at this point, I want to mention that what we did last week and what we're talking about right now pretty much is all covered in Chapter 8. Okay? We've done all of Chapter 8, I believe. Actually, that's not 100% true. There are 3 things in Chapter 8 that we have not discussed, and let me tell you what those are. But with this discussion, you should be able to read it in the chapter, take notes on it, and be able to understand it. Let me explain why. Atomic radius. We have discussed atomic radius and the trend on the periodic table to a point where I do believe that you have a good, firm understanding of what's going on with the Coulombic attractions of all of it. Then there are 3 other properties that all elements have that are affected by the atomic radius. Those are, if you want to write them down, electronegativity, ionization energy, and electron affinity. I will repeat those. Electronegativity, ionization energy, and electron affinity.
Ionization energy?
Correct.
Electron.
And electron affinity. I will write affinity on the whiteboard.
and the electron affinity?
So electron affinity, ionization energy, and electronegativity.
You want us to take
Wait,
notes
what
on
are
all these,
those?
correct?
Well, I want you to take the notes on all of the stuff that's in chapter
Right, what specifically?
8, but I'm letting you know that there are 3 things in chapter 8 that I'm not going to discuss in class, because after our discussion with atomic radius, and when you read through those 3, once you find out the definition of electron affinity, electronegativity, and ionization energy, you should be able to use your understanding of atomic radius to explain what the trend happens to be on the periodic table based on those terms. Questions on that?
Wait, what are they? Like,
Electron affinity,
no, like.
ionization
like
energy, and
what-
electronegativity.
like what is-
It's
like
called the periodic trend.
characteristics.
They're called the periodic trends.
Oh,
So the periodic trends that you should be able to discuss and understand based off its atomic radius end up being electronegativity, ionization energy, and electron affinity. And you should be able to explain all of that based off of the atomic radius itself. Sweet. Questions on this before we take a brief pause? I'm going to take a brief pause of about 1 or 2 minutes so you can let your brain relax.
back to my channel.
How fast
Chapter 7 is talking about the electromagnetic spectrum, and we probably
You guys remember the song?
talked about this.
Yeah.
That was the song.
Oh, Tom's.
Mr. T was so confused. He was just,
Wait, Tom, shut
It was like, what is this song? We were like,
Okay.
hey.
yeah, like what?
Radio
He played the wrong one.
Microwaves.
Okay.
You all set? Did you get out of your system?
X-ray.
I don't think so. Should I find it?
Yes.
Yes.
Okay, we will later. All right, so moving on.
You gotta play the right one. There's one that-
There's a wrong one?
Yes. Yes.
Because someone knew that like all chemistry teachers would play the song, so they made like a very similar.
So like there's no
version.
noise at the beginning, it's like really quiet. So like you put the volume all the way up and then all of a sudden it starts playing like bass.
And the rap song.
Got it.
That's so funny.
Moving on. We've talked briefly about the electromagnetic spectrum before when you did the nuclear chemistry portion. Right? And with that, we had talked about ionizing radiation versus non-ionizing radiation. And not that you necessarily have to have the electromagnetic spectrum itself memorized. If I were to draw a line approximately right there, anything that is this way versus this way. This way is non-ionizing radiation. The other direction, going in higher energy, is going to be ionizing radiation. Meaning anything that's going in that direction means we're able to strip electrons off and change the actual chemical nature of that substance.
Whoa.
Okay? Anything that's less than that, all you're really doing is speeding up the particles or slowing down the particles and basically adding energy and heating them up. Yeah.
How about an intense, like very, very intense, like concentration of radioactive?
Okay, so at the same time, does that mean that these other ways cannot harm you? No, you can blind yourself by looking into the sun. Right? So I'm not talking about the idea that these things don't do damage. I'm saying the type of damage is being done on the high end of the scale ends up being ionizing radiation, where at the low end of the scale is going to be non-ionizing radiation. But non-ionizing radiation can still do damage.
So non-ionization radiation cannot ionize no matter what the concentration of it?
Correct.
Okay.
So what will it do instead? Well, most of the time it just turns and heats you up. You know, sticking yourself into an oven is not a good idea. Okay?
What? When?
So, and that's, I mean, in general, that would be infrared radiation, and that will cause you damage overall. Ultimately, what I want to make sure that you understand, though, is when it comes to this particular chart, this end is low energy, and this end over here is going to be high energy. Okay? You good with that part so far? What's happening to the length of the waves as I'm getting further and further this direction? Smaller. So this is going to be small wavelengths. Small waves. Long waves. Okay? The other portion of this that you should notice is the frequency. Frequency is how often you get a wave. Which one of them has a greater frequency? Right side has a greater frequency, this side has a lower frequency. So this is going to be large frequency. And by the way, the frequency symbol ends up being nu. For those people who want practice on how to write new,
It's a question mark.
yeah, it's kind of like a sideways question mark. New.
New.
Greek letter new.
It's like a
New. And you. Okay, so
It's that stands
we
for-
have large frequency that side. This is going to be low frequency on this side. Long wavelengths, small wavelengths on the other side. Out of this entire spectrum that's up here, which one of them can we see?
Visible spectrum.
Visible.
Visible spectrum. And I know that just seems obvious, but the visible spectrum is the only part that we have the ability to actually perceive when it comes to our eyesight. We don't see radio waves. We don't see
That'd be so
gamma
weird.
rays.
That
Right?
would be so
It
You walk
would be
outside
different.
and you see it.
Well, you would see something different. We don't know exactly what that would be. Do we have ability to detect those things?
Yes.
Sure. If you want to detect radio waves, break out your radio, and actually you can dial in the frequency itself and be able to pick those up. Out of all this, one of the ways that we've actually been be able to determine the interior structure of the atom is from the light that comes from different atoms.
This is like when you
So this is where I'm going to
The
draw your attention to the
electron
back of the room.
and stuff.
This is the electron configuration in chapter 7. So what I'm going to give you is a box. And the first thing I want,
these
I'm going to get these boxes back, of course. But when I give you this box,
Is it a black box?
Is it a magic?
I hate
Is
these
it Pandora's
boxes.
box?
It's so
Stop
hard
it.
to read them.
first thing I'd like you to do is take a look at one of the fluorescent lights to see whether or not you get the entire rainbow.
Oh god, I feel like I'm going to blind myself.
Wait, how do I?
Oh, I see it.
Oh. Wait, I don't get the whole rainbow. Wait, do I? Am I supposed to?
Yes.
I think you're doing this wrong, buddy.
What am I looking for?
You're looking for a rainbow.
I see 7654.
Great, and that's where you should see the rainbow.
I see the rainbow now.
Good.
I was looking through the wrong place.
Not fair.
So, let me make sure. I'm
I
really
see it
sorry.
right above the 7654.
Yeah.
Do you see the range of light? Not necessarily that you can differentiate the colors, but can you see where the range of light happens to be showing up? Let me show you, by the way.
Yeah, it's like
Folks, stop
bars
looking
and
through and
like
take a look at me.
and then, like, lighter.
You can see the bars.
What you'll notice that
Oh, wait, I do see some. I see blue and what is
I see God!
We hear the
Yeah, the first time I was looking through here. That's
Well,
why
I could see.
yellow.
Okay, so let me get your attention, folks. Taking a look at what we got here. You'll notice that there ends up being a slit on the far left side of the box that I'm showing you. There's also then this other window that's on the other side, and this window on the other side is really where you're going to be seeing the numbers. What is going to break apart the light itself is this slit. The waves are going to be, actually the light is going through this will then turn it into the rainbow and then reflect that rainbow onto this portion that's on the other side, and then we can actually even measure what the wavelengths happen to be based on the numbers that are listed there. That said, right now if you were to look at just regular ambient light, you get the full rainbow, right? The Roy G. Biv. And what I want to point out once again, go ahead and put the boxes down for a moment and take a look at me. Up here, you've got red being low energy. We got high energy. Again, the same system of low energy, high energy, low frequency, high frequency, long wavelengths, short wavelengths. Same thing's happening just over a very narrow range. So looking at this entire range of the electromagnetic spectra, this sliver is what we can perceive, right? At least with our eyes. So how did this ultimately help us figure out what's going on inside the atom itself? In the back of the room, I end up having a device. And I'm going to have somebody... Ooh, I probably should unplug. There we go.
That'd be still a good idea.
And if we head back here... What I've got is this box. And inside of this box is a power source. And I want to start off with this element. This element is neon. So this is literally what is referred to as a neon light. Why? Because it has neon. And light is being generated from the fact that we're running electricity through it. Go ahead and run, or take a look at it through the box that I gave you so you can see the rainbow that's being given. You want to make sure that the slit is on the left side and then the gradations are on the right side so you can see the full rainbow. You'll probably notice that there are some very distinct and separate lines.
You want the this live on the left side, right?
All those very distinct and separate lines, you'll probably notice that there's some intense greens that show up. Do you notice the intense greens that show up?
No.
No?
It's like,
I see it. I see like red, orange, yellow, and like barely green.
You got it right.
Yes. Like that? Yes.
How many people can see the green?
Oh, I see something.
Yeah.
I don't know.
Okay,
what.
you see the green. There's probably good, very strong lines of red, a few of yellow, and a couple of green that are in there that you might be able to perceive. There might be some that you can perceive that are blue. So far, so good?
Yeah.
Questions on those? All right, so then the question ends up coming from, where are those energies coming from? All right, why is it that we're not getting the full rainbow? Why are we getting very distinct lines or spectra rather than the full rainbow? And what ended up being determined is that we're exciting the electrons on atoms, and those electrons are going from one energy level to a different energy level, and then falling back down again. And we'll take a look at that in just a moment, at least on a theoretical basis. But let me go ahead and show you a different element. This ended up being, once again, neon. And let me show you what hydrogen looks like.
Oh yeah, I remember doing this one with like the glasses.
Yeah. These are blue.
What is that?
Actually, that is not the hydrogen. At least I don't think it is.
Yellow, red, green, and blue.
But it's like all spread out.
What color is
It's
that?
like 3 distinct lines. Or
I wanna
four.
say
4.
pink.
It's like pink, but like barely, barely.
Oh, I see. A blue line.
By the way, what element is this?
It's like 4
I see it
distinct
sealed in
lines.
blue. I don't know what the last one.
All right. Try everyone. But you'll notice that this one was completely distinct from the last one we looked at.
That's cool.
That's up for what
I think that one might be mercury.
Oh, that one is 3 distinct lines.
is
Yellow, green,
Yeah.
purple,
I got like orange.
and like a
I got like orange.
I believe that one ends up being hydrogen, actually. Do you get? There's a very distinct. How many? What did people get for the distinct lines?
Like tan, green, and
So by the way, that tan is probably on the orange side. You got that distinct green, and you've got a blue in that, correct? All right. So when people started looking at this and getting the data that they ended up finding initially, they're just like, okay, why is that? Why is it that we're getting very distinct lines and rather an entire rainbow? Where is that coming from? If you take a look up at the smartboard, I ended up bringing up a different website that ends up having the ability for us to be able to look at the spectrum of the different elements, at least not all of them, not necessarily all of them, but a good sampling of them. So what we've got right now is all of the lines in the visible spectrum for neon. Do you remember how you saw 2 side-by-side green ones that were pretty intense? And then you also saw a few of the yellow ones? If you actually had a very high resolution or very strong source, you'd be able to get this entire intensity from it, and you'd also have better equipment. I mean, because literally, what are we using? We're using a plastic box and a prism, and a paper prism that's just stuck on the inside of that portion. Okay? And we were still able to see all those distinct lines. If we take a look at hydrogen, hydrogen doesn't have a whole lot of options. Okay? By the way, we ended up looking at mercury. We did not see the hydrogen one. I'll see if I can find the hydrogen one and put it in the box in just a little bit. But you'll notice that we end up having exactly 4.
Where's the fourth?
it's like
The fourth one is really, there's this one that's super dark blue, and then there's a violet one that's here. This one ends up being the light blue, and then we have a red. Which one do you not see?
The dark blue is completely not there.
Yeah. The dark blue, there is, the difference between the dark blue and the black is difficult to detect. Right? So do you see at least 3 of the lines?
I see 3, yeah.
Great. So with those 3 lines, we now can actually measure those at because we know what the rainbow happens to be and what the wavelengths are, we know what we have in their values. Which now means we could actually try and translate that into energy. But that energy had to come from someplace. So this is where the discussion from Chapter 7 now comes in. And let me slide this over this way. And so let's say that I have a nucleus. Sorry for drawing it so large. And here's hydrogen. How many electrons does hydrogen have?
2.
One. Has 1 electron. One of the reasons that oftentimes we like to look at hydrogen is because it has the most simple effect that we can actually look at. What happens if I excite that electron? Is it going to stay in the 1s orbital? Not if we add enough energy. If we have enough energy to it, it's going to actually excite it. What could it then potentially do?
Get off.
And go where?
Space. Or
Okay, it could be so high that it ionizes and the energy is now completely off of the thing. But what happens if we add just enough energy where it doesn't fly off, but it just gets further away from the nucleus? It could go to the 2s, or the 3s, or the 4s, or it could go to some other one of those other energy levels. So, if I've got this as, let's say, the 2nd energy level, this as the 3rd energy level, and this as the 4th energy level, what could happen is that this electron could get enough energy from the electricity that we're running through it and pop up, let's say, to the 4th energy level. Was that exothermic or endothermic?
Exo. Wait, relative to the atom or relative to the other?
Relative to the electron.
It'd be
To go from a ground state to an excited state. Is that
Endo.
endo? You have to put energy into that electron to get it excited to kick it up to a higher energy level. We would be so far on that part.
Yes.
All right, so we had to add extra energy to make it happen, so it's endothermic. What happens when it starts to slow down again? What's going to happen to that electron? It's going to be exothermic, and that electron is going to drop from the 4th energy level. Possibly it'll drop down to the 1st. Possibly it'll drop all the way back down to the 1st. Where else could it go? Could drop down to the 2nd. Could drop down to the 3rd. Well, so far so good. Okay, so if it dropped all the way down from this 4th energy level all the way down to energy level 1, is that going to release a lot of energy or little energy? A lot of energy. If it releases a lot of energy, this is where we can go back to this idea. If it releases a lot of energy, is that going to be at a high wavelength or low wavelength?
high.
Let's take a look. If we're talking about wavelength, we've got the higher the energy, the smaller the wavelength. We got the higher the energy, the larger the frequency. So if we're talking about high energy, what are we going to end up with? Small wavelengths or high frequency. So that would give this, a high frequency would be something like this. And that would be the photon of light coming off. Is this sounding familiar?
Wait, what? Doesn't an electron produce 2 photons?
If you were to annihilate the electron, yes, but we're not talking about nuclear annihilation.
So where is the photon like stemming? Like where is it?
It was at a high energy level, goes to a low energy level.
So that energy, okay.
So now, if I can measure this energy, what do I now know? I know the amount of energy that it took to go from the 4s down to the 1s. And if I can measure that energy, I can now also start to measure that distance. I can start getting a better idea of what the atom itself looks like. All from the fact that I got 1 packet of light out of that. Yes, sir?
So would this value ever go into the negative? And if it does, then do we assume that it's a low frequency or a low?
It can't go negative.
Okay.
The reason it can't go negative is then well, right now, it is exothermic, so it's all negative.
Right.
From the perspective of the electron.
Right.
But I can't have a negative wavelength because that means it's going to be endothermic and energy is going into it.
Right.
So if this electron's at the 4th energy level and drops down, energy is being released.
Okay.
Is this going to be at a high or low? It's at a high energy, so that means it's at what type of wavelength?
If it's at a high energy.
Small wavelength. Okay. So what about when it goes from the 4th energy level down to the 3rd energy level?
Then it'll be at a low wavelength.
So then it's going to be a low wavelength. No. High wavelength, low frequency. So let's take a look at the relationship once again. Hopefully people wrote this down. Low energy, low frequency, long wavelength. High energy, large frequency, small wavelength. So if you've got a big drop in energy, you are going to have a short wavelength or a high frequency. If you have a short drop in energy, you're going to have a very long wavelength and a very low frequency. David?
Since every atom has its own unique atomic radius, every single long wire jumps from one energy state to another one will be unique to itself, right?
So if we go back to what we were just looking at with this, why does hydrogen only have a few lines? Well, how many electrons does it have? One. How many places can it go? Not that many. Does that make sense so far? What happens when I hit magnesium? I have more possibilities for where that electron can go to. Now, one of the other things that will happen as well is that can these waves that we've just been talking about be out of our ability to see it? If it was so high, it would go ultraviolet, we wouldn't be able to see it. If it goes so low, it's going to go infrared, we're not going to see it. And it actually can even go into the X-rays and beyond higher, or not necessarily too much further beyond, but it can actually go also much lower and go into the infrared range. So what ends up happening is that each one of these elements, pick an element. How about lead? There we go. There's lead spectrum. This spectrum is unique to lead. So now let's say that I end up casting my telescope out into the space and I find a particular star and I'm able to get the light that's coming from that star. And I'm able to separate it out and I'm able to get exactly 600.2 nanometers for the light that I get. And then I confirm all these other ones. What have I now confirmed? There's lead in that star.
And
Yeah.
if the planet begins to eclipse it, you can see the light reflecting through that atmosphere, and then you can find out the contents of the atmosphere, right?
Correct. So the way that we have gotten all of our information from space has been taking the light and doing something with the light.
Wow. We also take into account redshift and stuff